There is one interesting way of looking at this whole stuff, which was also suggested by one of the student here, is be anyway while fitting your meta model or your surrogate, constructing your meta model or surrogate, there are some error metrics that come with it, okay, like as simple as R squared errors or prediction variance that we have discussed in Kriging. Okay. We could probably use that. So, we are going to look at those kind of techniques now, how to go about it. Okay. So, this is called error based exploration. Here the discussion is focused on the Gaussian process, but at a later point people have also shown that the error metrics or the uncertainties in the predictions from one model can also be imported to another model. For instance, in Kriging you have a Gaussian predicted variance. For instance, a polynomial response surface does not explicitly give a prediction variance, though it kind of implicitly gives it in terms of R squared. So is the case with RBF, let us say. But what you can still do is you can kind of make a one-to-one match, and then you can import the uncertainties that are associated with your predictions from one model to another model. Okay, it is doable. So, let us limit our discussion in this particular session with respect to Gaussian process, but please understand it is scalable or it is adaptable to other meta models as well. What we are trying to focus on is this particular equation, which I might not have discussed while talking about the Gaussian process in general. Okay. But this is usually also called your mean squared error in this particular case. We also call it the predicted variance. If you remember the discussion that we had about having points and fitting lines to it, we always called something the R squared error. What did the R squared error mean? It meant if you had a set of points, the best minimal thing that you can do is to have an average. It is just going to compare how good is this line with respect to the least thing that you can do. It is just going to take the average and compare it with that. If you go back to your expression, that is a way to look at the expression. Okay. There is all errors are there, and finally it will compare those errors with respect to your mean. Okay. Now, what this R squared also says is how much of the variance is explained. The line passes through the set of points, and how much of the variance or the variability in the points does this line capture. There are always some variability that is not captured, that is what R squared says. So, if it says R squared is about 0.9, then it says 90% of the variability is captured by this expression. If you say no, I want 95% variability to be captured, then you will have to either change your model or you need more samples. That is the point. So, probably we could use this metric to drive our understanding about the surrogate also. You construct a surrogate, how good is my prediction? How good my prediction means what? Let us say that you predicted your y to be, I do not know, 80, then 0.9 means what? It means that you have only 90% confidence on the value of 80, which in one way of looking at it is this can vary anywhere between 7.2, which is 90% of this guy, 72, not 7.2, 72, and the other one is 1.1, so 88. So, it can go up to 88, okay, 10% this side, 10% that side, that is all. So, this is the idea that you want to have. So, if I had a function like this, let us say, and then for whatever reason, let us not worry about optimization, and then let us say this is the point that I got, this is the point that I got. I just need to appreciate that there is a band that is associated with this. The curve could have been here or it could have been here, that is what this point says. So, this is the predicted point that we are talking about, that is what this y hat is, and this is your lower bound and this is your upper bound, that is all we are talking about here. Sorry? But R square is overall, so it is like a global error. Correct, but that goes across. This is a global error metric, correct, that is one, it is in an average sense, that is what it is. So, it will go all around. Okay. That is an interesting point, because R squared what it says is you can only construct a curve like this. That is the problem with R squared. Okay. So, but that is not true, that is not true, because if we, even if we go to our example here, okay, at this point, at this particular location I have huge variation in my predictions, whereas at these locations I have only very less predictions. So, it is an interesting point, because if I know this a priori, not throughout the same difference, then it will be good. So, that is why the press error or the cross validation errors are more relevant than R squared. R squared is good, R squared kind of gives you an entire idea, gives you an idea about the entire design space, how good the meta model is in a generic, in a global sense. But press error kind of gives you the local, what are the errors with respect to the local basins. Okay. So, basically you do not have to worry too much about this expression per se. I am going to give you a pictorial depiction of this, but before we even go into this stuff, this is basically what it says is this is your prediction variance, because we are going to talk about a Gaussian process here. So, it will have a mean and a standard deviation. So, this is the standard deviation that we are talking about, and this psi is nothing but your correlation, that is what we are talking about. Okay. So, that is what the Kriging kind of thrives on, the correlation information. So, we are using the correlation information here to come up with the. So, what is the idea about this prediction variance? So, what prediction variance says is, if you take this example for instance, the same thing that I told you, it will predict this point corresponding to 0.8. In addition to that, it will also tell you what was my S squared at 0.8. And in this particular example, your S squared, which is the variance, and you are predicting that. So, it is a prediction variance, is likely to be large compared to the prediction variance here. Isn't that an interesting point? It is an interesting point, because you are predicting, and I am also telling how good your prediction is. That prediction is usually governed by what one of the students told is the change in the trend. You do not go and see whether your trend is changing like this or changing like this, you look at your correlation information, that is all. So, that is why Kriging is very interesting, because it finds the correlation between the design variables themselves or the input variables and with respect to your response as well. So, this particular figure gives you the plot for the prediction. It is not a prediction variance, but it is a square root of that is what we are presenting here. Okay. So, this is x and this is s of x. I have plotted these two. This is the actual function which we do not have, but for the sake of discussion we need to have that, and this is your corresponding s. As I told you, you can see at this particular point the prediction variance is large, and at these locations, yes, there is a small prediction variance, but it is really not showing up. If you zoom, you might see it as slightly. Okay. So, what do you think could be a good idea here? Because this is an estimation that is a byproduct, this prediction variance is a byproduct of your Kriging construction. Once you construct your Kriging, this comes as a byproduct. But does this information tell you where you want to put your additional point? That's the whole discussion that we are having here.
If we are interested in counting, then not necessarily. But exploration, yes.
From an exploration perspective, he says you can put points based on your this particular graph, which is your S graph. Where will you put it?
Where is the confidence is like low?
The confidence is less. That is where I will put my next sample. Confidence is S refers to S being, confidence being low refers to S being higher. So, obviously in this location I will try to put my next point. So, this is logic. So, I put a point here and then I will get a new point here, and my function might not follow the real function, but then it is likely to do. So, it is a nice thought. Okay. So, we could choose the maximum prediction error as an infill criteria, but in this particular case actually there is some plotting error here, or it is very small, we need to zoom in here, and I could have multiple peaks also. Then what do I do? Do I add as many points, or what is the story? So, but then you can still use the maximum prediction error as an infill criteria, but this is equivalent to only filling up the gaps. Again we might go to ground zero and ask, what if I started with 8 points to begin with? Okay. And also the question is, when do you stop adding? Because what is the guarantee that you will not get locked in a local optima? You can always say, oh, I think this could be a local optima, is not real convergence. So, should we just throw some points 1 meter away and check? And then maybe you get into another local optima. There is no guarantee that that local optima is going to be better than this local optima. Then it also introduces another question, what happens if you throw another 0.5 meters in between these two? So, all these questions are there. So, the other thing is, when do you stop adding? As he pointed out, this is more from an exploration perspective, and then I want to make sure that increase my confidence on the optima that I have and start exploiting. So, this is one way to look at it, it is still not a bad way. The other question is that I told you in the beginning is, I want to both balance exploration and exploitation. I want to build a model that will tell me, if I am an expert, I will tell you, oh, I know that, okay, this is the zone of interest, now I want to exploit. So, my model should give me the weightage for exploitation, or I say I am not sure, it could be here or there, then the model should give me the weights to explore. So, it is a good idea to have a model that can balance both, or it should at least have the elements of both exploration and exploitation, right. So, this we have already talked about, the estimated error or the prediction variance, the uncertainty in the prediction can be modeled. Here is a very interesting concept, please stay with me, this is a very interesting concept. Okay. You remember this that we have discussed? We always comfortably say y equal to y hat, that is not true. Y is modeled as y hat plus error. Please recognize there is a error, the error guy is a culprit, or he is the hero, whatever. Okay. So, this is important. If you appreciate that, then all this r squared and all that makes sense, your press error, everything makes sense. Now, what we are going to do is this prediction variance in one sense is this guy. What I am telling is, you go to this, go here, what I am trying to tell you is, if this is what you are predicting, it could either be this or it could be this, that is what that small error is. So, y hat plus error, what is this error? 10%, but please remember it could be plus or minus, that does not matter. So, it is a band around it. So, that is what that error says. Now, here is an interesting concept. What people try to do here is, comes from the statistics, and if you recall the way that we have discussed polynomial regression is, there is some characteristics to this error. What is that?
Mean is 0.
Okay. Then this guy is normally distributed with a mean 0 and some standard deviation. If you know the standard deviation, that is all I am talking of. This is the one that I am talking about. This is my prediction and this is my standard deviation. This is my prediction, this is my standard deviation, and these are my points. You see these points, the blue points are my actual points. There is always an error between my prediction and my actual values, that is one thing, and I locate. So, the idea is it follows a normal distribution. When I say 0 mean, what does it mean? It is located at my prediction. My prediction is the mean value of that variation, of the error, and then the standard deviation is something that you want to compute. So, this is in a statistical sense, but if you want it in a bound sense, imagine that I am taking a 25th or a 25th and a 75th percentile, whichever way you want to do. But the idea is there is a statistical distribution that covers this variation. So, the same idea is going to be used here. So, what we are doing is, we are taking this prediction variance and we are saying this is a realization of a normally distributed random variable y of x, which is what you are trying to predict here. with the mean y hat of x, which is what you have taken for a particular point x, at x what is my y hat, and some variance. What is this? This y hat you will get from your model, this s squared we saw through your correlation, you can get this information. Okay. The only catch now is we are modeling this as a normal distribution. So, the moment I say this error is follows a normal distribution, then you can inherit all the properties of a normal distribution. Usually with a normal distribution or any distribution, what do you do? We always construct distribution only to estimate probabilities. So, now you can generate a very interesting perspective of it can give you probabilities of something. What could be that something? Because we are talking about errors. We are assuming that the error is normally distributed. I know the mean and the standard deviation, only two parameters are required for me to describe a Gaussian distribution. So, I have that. It can only give me probabilities of the error, but we are really not talking about errors. If errors, we are talking about errors, but from a perspective sense, we are also seeing, or we want to use errors in what way, such that from a prediction perspective, can I increase my meta models fit in a better way, which means if I add one more point at some location, is there a likely chance my overall error will go down, or at least the error at that point will it go down? Please understand that is a very powerful statement, because there is no guarantee that your error will go down just because you add one more point right next to that or around that zone, whatever it is. There is no guarantee. It could go bad, it could stay the same, there is no guarantee about it. So, it is very interesting to see this prediction, the whole point of prediction, though this is interpolation, we are not even talking about extrapolation. Extrapolation is totally a different ball game. We are only talking about interpolation. Even in interpolation, there are these challenges, and something that can tell you a priori that if you do this, it is likely to happen. If you go to gym for 30 days, you are likely to lose 2 kgs of weight. No one can guarantee that you will lose 2 kgs of weight. There are other factors why you are what you are. Okay, just because going to the gym you cannot reduce 2 kgs of weight. But if I analyze all your physiological parameters and all that, and if I tell you, okay, if you are going to take up this particular aerobic activity, it is likely minimum you will reduce 2 kgs. You can achieve 10 kgs also, but minimum I promise that you go take 2 kgs. That's what this is. Okay, it gives you that kind of a guarantee. So, the y-x again could take different values based on the size of the variance, that we will see, there are pictures. Okay. But the way that what we are trying to do is I kept telling you that we are looking at balanced exploitation and exploration. So, I am trying to construct a lower bound or higher bound if you are talking about maximization. I am telling you this is the minima, but how low could the minima be if it was an accurate representation, that is all we want to know. So, what we are saying is this is your prediction y hat, and there is some standard deviation. So, I am going to subtract the standard deviation in this case, plus or minus, right. So, I am going to subtract the standard deviation. Please see, this is your function and this was my minima, but this is from an approximation. So, by how much could it vary, I would only be interested in this direction. It can vary on the other side also, then it will become positive. So, I am only interested in the negative side. So, this is the standard deviation. So, it could be 1 standard deviation, 2 standard deviation, 3 standard deviation. For people who do robust design, for instance, there are two things. One is your mu and the other one is your sigma, because we assume a normal distribution in this particular case. What we do is you want to minimize the distance between the mu and your target, and at the same time you also want to minimize your sigma, and oftentimes the target is not given. And we say I want to maximize my mu and also the standard deviation of minimize the standard deviation of my sigma. Assume that you are talking about profit, you are trading share market, obviously it is varying, but you want to pick up your portfolio in such a way that in an overall sense the average profit that I make should improve, at the same time the variability should be reduced. This month I make 20 lakhs, next week I make next month I make 20,000, that is a large variability, then I cannot plan. Okay. So, I want to minimize the variance, at the same time I also want to improve my profits. From a mechanical engineering or a design perspective, this is called the robust engineering concept, right. So, you want to if you take a distribution, you want to move this distribution which is improving your profit, and you also want to make this distribution as thin as possible. This is usually written this way. This k gives you a weight for your sigma, how important your weight is. And from a 3 sigma or 6 sigma perspective, the usual robust design in mechanical engineering is 3 sigma is what we take, but you can make it 0.5, you can make it 6, whatever it is, depending on what is the importance that you give for your variability. It is a similar formulation here, that is all. Only thing is we are explicit here by saying it is minus a sigma, I want only the lower bound of it, I am not interested on both sides, that is all we are talking about. So, this is interesting because if your a goes to 0, then your lower bound is nothing but your y hat of x. This is just the point that you are going to predict. It is a pure exploitation in this case. And on the other hand, if you are making this guy to be infinity, a to be infinity, then this guy is losing its effect, which is pure exploration. So, you kind of come up with a formulation, I would say. It is not even a formulation, it is just an expression, because all these are already there. Okay. It is just an expression or way of expressing it, so that we can have both exploration and exploitation. By playing around with the value of a, you can balance both exploration and exploitation, and it also tells you what would happen. So, then if you believe that it could be of interest, then you explore, otherwise you leave it. That is the interesting part. But the interesting point of this previous expression is there is no clarity on how someone would choose a. But if researchers continue to do or accept the previous model as a good model, they would have had a thumb rule by now. Okay. But there were better approaches later, which we will discuss again. That is why I gave the robust design example. There are also other ways of looking at robust design. For instance, you can do an SN ratio, okay, which is nothing but signal to noise. Noise is nothing but your sigma, which is in the denominator, and signal is in the S or the mu is on the numerator. You can do that one also. This is just to give you an idea. You see this red one, that is the RBF prediction, and these are the lower bounds that we are talking about. If I take 1 standard deviation, then this is the blue. If I take 2 standard deviation, this is the 1. If I take 5 standard deviation, this is the 1. But always please remember that you do not have the black curve. So, do not say, oh good, I could have taken the green, which is 5 standard deviation. 5 standard deviation is too large. The point is, if you go, it is likely to capture, but how do you know that you will go that far? There is no way, that is what it said, right. I do not know whether to choose 1 yes or 2 yes or 5 yes, I do not know which yes to choose. There is no way that I can do that. Probably you could use the same S squared information to say, okay, this could be it, or this is good enough reason. Let me ask you, I should not be giving out everything. Let me ask you, this is the one, right. With the same expression, you can still identify region of interest for your infill sample. How do you do that? From this plot, you can tell me. Because currently with this thing, what we are trying to find out is this is going to be an optima. But it does not stop here. You are not doing any additional, you are only doing algebra, you are not doing any additional computation, and you are able to get these 5 graphs, and you can get up to 10s also. No. Based on what? What will be the criteria for you to put a point anywhere?
The LB, lower bound value variation. If you change the A value, correspondingly LB value changes at each point.
Good. Okay. What you need to appreciate here is, these 3 graphs are not only in this location, they are running across your function, but only in this region there is a large difference between your 1s, 2s and 5s. That is no wonder, because I have accumulated my points here. That does not matter, given the set of samples. If I removed all these red points also, if I removed all these red points here and I ran this, I would have had something like this for 1s, 2s, sorry, it would not have been above the function, it would have been below the function. but the variation would have been much lesser, it would not have been as big as this. So, probably we could use this and then tell, oh, this could be a region of interest where I want to add my point, but that is exactly what your prediction variance also says. So, we will see how it is can be used. That is exactly what people say probability of improvement. It is not only just prediction variance, but as I told you, we are going to model the variance itself as a probability distribution. So, it is going to tell you what is the probability by which you will improve. There is no guarantee that you will improve, but I will tell you what is the probability that you will improve. That is it. If you say, if I tell you there is only 1% probability that you will improve, I will probably not invest in an additional simulation. Even if it improves, it is only 1%. We always believe that it is likely to improve, not really. Okay. So, that is something that you will have to ingrain. Even if it improves, it will only improve by 1%. So, you go to a gym, they say let us go for a 6 months package, 50,000 rupees. What is expected? I will reduce 1 kg. Now, unless you have surplus money to throw the cost, you will say, come on, I go on a simple dieting, I am very likely to reduce 1 kg in 6 months. What happens after that is a different story, okay? That is out of scope of the discussion for here. So, the point is, what is the probability of improvement? That is important. Okay? If you say probably you will reduce 1 kg, the way you are saying probably, instead I say 6 months, each month 1 pack, 6 months I guarantee that 90% you will get 6 pack. That is a good deal, but again there is some catch, right? You will have to do some dieting, you will have to drink this much of water, you cannot eat whatever, okay. Given all that, understanding all that, if I give that probably with your current discipline, you come to me, you pay 50,000, so that is a good deal, probability of improvement is high. Okay. So, it is very interesting to have that perspective. It is again probability only, after 6 months there is no guarantee that you will get 6 pack, it is a probably you will get a 6 pack, okay, provided you do all these stuff. That is the same idea here. In this entire search and infill, you are searching your design space and then you are finding a location where you will put another point, which is what is the infill point, right. The idea is to place the infill point at a value at x such that you will find a even better minima, correct. I want to put a point. What is my overall idea? With the initial set of samples, I am just saying, okay, or I will go to another graph. Yeah. So, let us say don't worry about what this function is and all that, okay. I am just taking a graph. Let us say this is the initial set of points and let us say this is where my initial first point optima is. When I put the next next infill point, what is it that I am hoping? Wherever it is, I am just hoping I will find some point that is lesser in terms of value, because we are looking at minimization, okay. So, wherever you want to put, you put, but I am hoping that the point will lie somewhere below this line. So, now you can take that as a criteria to drive your search. Yeah. So, that is what we are going to do here. A value of x that will lead to an improvement on the current best observed, not necessarily the best, of course you do not know. With the set of points, with the meta model that you have, this is the best. Now, if I put one more point, it should better my meta model, or that is an exploration perspective. From an exploitation perspective, I should be able to find another point that will be better than this point. In a minimization sense, it should be below the point that I have found. That is should be the overall goal. But again, you only hope that it will. So, you will run this as a criteria, and when your standard deviation goes 0, you will go to the same point, that is all. So, meaning your prediction variance goes 0 at that point, that is all, okay. Now, what we are saying, since your y hat is considered, that is what we said, right, y of x is random. Since y hat is considered random, the probability of improvement, we are saying just y min, which is the existing best, minus some point, meaning some realization of this, you can just exchange y of x and y hat of x, does not matter, okay. Yes, this is nothing but a normal distribution thing, nothing but you can express this as part of your error function, okay. So, this I is what we are talking about here, okay. Y mean minus whatever that random realization is minus y hat, which is your prediction, meaning that should give you a positive value, otherwise there is no point, okay. A positive value squared and all that, and that is exactly what we are modeling as a normal distribution, okay. Do not worry too much about the expression per se, this is what the pictorial depiction of that, okay. So, this is your point, these are the points, okay, the circles are the points here, and I have fitted the black line, the black solid line is your true function, and this is your RBF function, the dotted line is your RBF function. Now, what we are saying here is, you see this particular point, this is your prediction, same like our regression, our polynomial regression, okay. This is the mean, it is located around this point, it is a normal distribution, this is the mean and it has some standard deviation. Do I know the standard deviation? I know, because it is the prediction variance. You do not stop there and say, okay boss, take this as your bounds, that is one way of looking at it, because this is your 10th percentile, this is your 90th percentile, you can still do that. No, I just do not want the bounds. Can I get some more information? Yes, I will tell you, if you put a point here, I will tell you what is the probability of getting a better minima, okay. So, what does that mean? Here is my this small dotted line, okay, this is what my minima line is, and the area intersection, okay, this intersection, because this is a curve here, the probability distribution curve, and this is my intersection, right. So, this shaded region tells you the probability of improvement, because what it means, this guy should go lesser than this line. What are the chances? Only this much is your chance. If that probability was very less, I would rather not invest. That again depends on the application, how expensive your simulation or your experiment, all that is, okay. So, part of the distribution below the dotted line indicates the possibility of improving on the best observed value. So, you can also plot the probability of improvement, but it is not a one shot, you will have to keep iterating and then keep improving, because as you progress every point you also have an estimate. So, you can go and reconstruct your meta model and then there will be a new probability of improvement with that. So, the highest probability of improvement, P of I means this is improvement and this is the probability of improvement, right, is in the local minimum in this particular case. It is the same plot. For the same plot, I am plotting the probability of improvement, okay. As you can see, the probability of improvement is very high in this location. That is true because I have a likely local optima there, and here and all I might not improve, there is not much of a variation because it follows the same function, okay. Then here there is a lot of variation and I will get a probability of improvement. Here it says for sure I have a large probability, but then one information is missing. What is that? It gives you the probability of improvement, sorry, by how much? You do not know. It said I will tell you, he said I will reduce the weight for you, in 6 months I will reduce the weight. If you are wise enough, you should have asked by how much. 300 grams is also reduction of weight, but I want to reduce 10 kgs. So, by how much, that is important, okay. So, can you get that? So, this is getting more and more greedy, that is the whole point of optimization, right. You do not want to do any additional simulation. Without the simulation, can I say will there be an improvement? Yes, there will be an improvement, but can you tell me by how much will the improvement be? Is that possible? Is that possible? How? Until this is okay, there is nothing new. It is just that I have shown you some nice equations and we pictorially and then conceptually we know this idea. But is it possible to tell by how much? Okay, you have about, in this case you had about 20% chances that, see what I am trying to tell is there is a 20% chance that your optima will get better. Here there is about, it is really not exactly that, but I am just saying, like 0.05 units compared to 0.2 units. Okay. But the gain here will be much lesser compared to here. Is there a way to do that? How?
the variance is high in that region
Hmm.
and not the local region, but the probability is, means probability of improvement is also high in that region.
Okay. Yeah, fine, you could do that. You could look at, but in one sense it is captured. Your probability of improvement kind of has your information, okay, the variation, but from a metric perspective you could use that. So, what he says is I could run what do you call prediction variance across, and then I can also look at the probability of improvement, and in this particular location I will say that the prediction variance is large and the probability of improvement is also large. So, then that could be one location where that is one thing, yeah. So, let us see what it is done, okay. So, though PI indicated where the improvement might be found, it does not show you how big the improvement could be, but it can be done in a very easy sense, because you are only going to look at your this, because you are modeling it as a normal variable. So, you are only going to look at the expected value of your improvement. See here what we are doing is probability of my improvement is what you are looking at. So, there you look at your expected value of your improvement, which is nothing but your average value, okay. So, you can just do this. So, this is your improvement y min minus y hat, and you are modeling it, of course, it is a Gaussian process, the whole thing that we are assuming. So, this will be your CDF and this will be your PDF. So, you are just expressing, provided your S is greater than 0, your variation should be greater than 0. If it is equal to 0, then there is no improvement at all, okay. So, this is holds good only if your S is greater than 0, okay. Just to give you an idea, if you are going to plot that, okay, very similar to our previous one, what did we plot earlier? X versus improvement, just the improvement we plotted, right, the blue curve, I remember, yeah, sorry, the variation, the predicted variance, okay. So, it will be similar actually. So, it is a good point that he made. You can see a small gap here, okay. So, this with respect to that, if you say, in that case you will have peaks in both here and there, okay. So, that kind of gives you the, at this particular point, if you add a point, I can expect, okay, a better improvement. That is the expected improvement idea. So, now just to give you an idea, it is not going to happen in a single shot, that is what I told, right. So, you expect an improvement, okay, it gave me 20% expected improvement. So, I am going to go put a point there, and then it gave you some improvement. Let us not worry about what the improvement, it is gave an improvement. The moment you have a point, you do not want to stop there. What you can do something better, you fit another meta model to it and then you see what happens. So, where do you stop? But in the process we will also see what happens. So, we take the same function, it varies between 0 and 1, just given a snapshot from the corresponding textbook. So, this is the function itself. These are the 3 iterations that we are talking about. It starts with zeros, I mean these 3 points, it started at 0.51, and then we found an optima, and then we put another point here. That is one way of looking at it, but that is not what exactly is happening. You also have an expected improvement. So, you take this graph, this is expected improvement. So, you go and put one more point here, that is what has happened here, correct. It is somewhere here. So, here you put another point, you fit another graph. You can see that the theta is changing here, the Gaussian process theta is changing here, okay. So, this is a new fit now. Now, I run another one. So, my expected improvement is moving to the right, the value is changing and it is moving to the right as well. So, obviously, here I will go and put another one. So, something very close to 0.5 you can see here, okay. Then I put another point here, the theta has changed, as you can see the theta is going down. Now, this guy went slightly to the left and he is becoming thinner, okay, not taller though, it is becoming thinner. As you can see, you also need to observe these values, okay. It is becoming thinner, but also shorter. Now, but that does not stop, okay. It looks like it is going to get locked in the local optima, but not really, okay. Now, this is 4, 5 and 6, okay, iteration 4, 5 and 6. So, what is happening is it came all the way to the left, okay, it goes all the way to the left, but suddenly there is also a expected improvement at the right end, okay, and then it keeps going, okay, and I am improving, I am giving up the number of points and the theta seems to be increasing, okay, and then finally it goes here, and then it goes here, and you can see it is e power minus 3. So, it is very small, but it is also almost equal to deterministic. It becomes a single point, which means your standard deviation is going to 0. That is your convergence criteria. Okay. This is just to give you an idea that it is not a one shot stuff. This is a simple problem. It is a very simple one dimensional problem, but you saw how many iterations we have to do, 9 points from the initial 3 points, no, 3, 3, 6, 8 points, 8 additional points you need to have, first 3 points after that. Okay. So, this is just to give you an idea, and people can iteratively add these samples, okay. But this is more from a one dimensional case. In n dimension, it is not going to be that straightforward, and you can also have what we call the island failure regions. Okay. Then you will have to see how you want to add samples, so that you do not want to get locked in one side of your failure domain or one side of your safe domain. You will have to take care of both sides, or both sides are n side, there could be n patches also.